If this is not your first time, kindly indicate. So it seems this is the first time for most of you. That's very interesting if you ask me. That's interesting. All right. It's oh, let's all right, sorry for that. Let's begin properly now. I want to believe the majority of you can see my screen. Please, if you can't see my screen, kindly indicate. But I want to believe majority of you can see my screen. Now, the whole concept of programming, this class is going to be very interactive. This class will be very, very interactive so that you all will be able to come along and understand what I'm trying to say here or understand what this is all about. Now, what we're dealing with here, what we're going to be dealing with here, has to do with computational thinking. Basically, it is how the computer processes what you give it, right? Now, you all know that the basic way we handle the basic thing we know about computer is that computer is this black box here. The computer is this black box here, whereby you give it input and it produces output for you. And this is the computer. So we are trying to decipher what goes on inside here and what this represents. Now, from this black box here, you can actually, this is where the algorithms, the programming, and every other thing flows inside, right? And before we do that, I would want to introduce you to something. I prepared a video. I had to go online to get the video, and it's just something that will serve as a motivation for majority of you all that are here. It's a minute video, so should hold on while I get it. So, all right. So this is from code.org, and I got it.
Access to a computer. My parents. I was in 6th grade.
I went to college, freshman year, first semester.
I wrote a program that played tic-tac-toe.
I think it was pretty humble beginnings. I think the first program I wrote asked things like, what's your favorite color? Or how old are you?
I first learned how to make a green circle and a red square appear on the screen.
The first time I actually had something come up and say, hello world. And I made a computer do that. It was just astonishing. Learning how to program didn't start off as wanting to learn all of computer science or trying to master this discipline or anything like that. It just started off because I wanted to do this one simple thing. I wanted to make something that was fun for myself and my sisters, and I wrote this little program and basically just add a little bit to it. And then when I need to learn something new, I looked it up either in a book or on the internet, and then added a little bit to it.
It's really not unlike kind of playing an instrument or something.
All right. So the point of this is to explain or to motivate you guys on what this is about. I believe most of you have submitted the assignments that was given, the holiday assignment that was given. Now, the concept of this whole thing is that you're not expected to know everything before you start working on some things. You're not expected to read up everything before you start working on some things, but rather you learn and you try to build. You go back to learn and you try to build, because in the end, this is a learning process. There is no programmer that still says that, oh, he or she knows it all, and he or she can, there is no need to learn anything new, because new technologies keep coming up, new languages keep coming up. You understand? So what we are working on, like I said, is we are trying to decipher what goes on inside here, what this represents. Now, if you recall, we know that in primary schools, the default way we do counting, like before we started to do the addition and subtraction, we usually count with our fingers, right? Please unmute your mic. I want this to be interactive. We count with our fingers, right?
Yes, sir. Yes, sir.
Yes,
Yes,
sir.
sir.
All right, good. Now, with just one hand, or with just the palm of your hand, how large can you count?
10,
No, I said just one, just the palm of your
5.
hand. 5, right? All right.
Yes, sir.
But everything is actually one after the other, right? Like 1, 2, 3, 4, 5, and that's it. For you to be able to move to 6, you have to introduce the other hand, or you start all over again and you count again from 1, 2, 3, 4, 5 to make it 10, right?
Yes.
Yes.
All right, good. Now, this is actually what is called the unary. It's literally what you time base 1. You understand? It's everything is just how will I put it? Sorry, the unary, sorry, is just base 1. Now, the way you count, according to mathematics, they call it decimals. You understand? But the concept of this whole thing is what gave birth to the concept of counting in computers, in programming. Now, we already know that the computer understands one language, and what is that?
Binary.
Binary. Good. Now, binary is actually basically binary digits, which are how many digits make up the binary digits?
0 and 1.
0
No,
and
2
1.
digits. Yeah, 2 digits make up the binary digits, and those 2 digits are called what? What's the general name for those digits?
They are
All
binary.
right. No, they're called bits. Zeros and ones. They are called bits,
Yeah, yeah, yeah.
right? They're called bits. Basically, they are short for binary digits. Bits is like short for binary digits. So they are called bits. And the binary actually comes in different ways. For most of you here have bulbs at home, sockets, right? The concept of sockets is simply on and off, right?
Yes, sir.
Yes, sir.
Yeah. The concept of sockets is on and off. The concept of the television is on and off. And to be fair, to be honest, even in your remote buttons, you get to see that button there. It's like a 0 and 1. You understand me? Most times you see like it's like there's a 0 button, there's a 1 inside. That's like the power on and power off button. If you check most of the remotes or the remotes that you have, right?
Yes, sir.
It's literally just a fancy design for your 0 and 1. Now, what will you say now? Looking at this bulb, is this on or is it off?
It's off, sir.
Is what?
Off.
All right, good. And off is what?
0.
0, good. And when it is on?
Just 1.
1.
1, good. This same thing, this is actually the way your computer handles information. This right here is the way a computer handles information. So it just thinks only in binary. Everything is recorded in binary. Your keystrokes actually come in binary before it is then displayed as your letter, as the letter you know it as. But these things move extremely fast that you don't even get to see it. You understand? Now, your when you look at your decimal, what you see here is 123, right?
Yes, sir.
Yes.
All right, good. But can anyone explain to me how this works? In primary school, we're taught something that is usually the units, the tens, and the hundred, right?
Yes.
Yes.
Okay. And because of this is decimal, it means that this is in base 10, so everything is going to be what?
From
Less
0
than
to
0 to
Zero
9.
to what?
Um,
0 to
0
9,
to
and how many digits 0 to 9?
10.
10 digits, good. And now, doing this, how does this work? The tens and units work here.
Sir?
120. We have 123. Can you explain to me how this works?
It was converted to binary.
Nope, that's not it.
how does it?
Okay,
Sorry, sir, can you repeat what you asked?
all right. I'm asking now. I said, can you explain to me the concept behind this? You know, the concept behind these digits 123 or 123.
100 plus 20 plus 3.
Exactly, exactly. You understand? And this actually is shown here, right? 100 times 1 plus 10 times 20 plus 1 times 3. And if you observe, because of it is in decimals, the distance from one digit to the other is 10, right?
Yes.
Right?
Yes.
1 to 10. Here we have the same thing. It's in multiples of 10, sorry. Multiples of 10. Stand from 1 to 10, 10 to 100. What is going to come next is what? After this 100, if we were to have a different, another number here.
8,000.
1,000. Good. And now, knowing that this is the ones place, this is the 10 place, this is the 100 place, we can now put in numbers here. So how high can we count with just these three places that we have here? Can anyone tell me how high can we count?
So let's say times 9 or something.
Not exactly. It's close, but not exactly what I'm looking for.
999.
Exactly, that's the answer. You can count 999, of which, when you do that, the nines turn to 0 again, and you have, if you decide to add a new digit, you have 1,000, right?
Yes,
Are you
sir.
following? All right, good. Now, here we have this. Okay, we already know this. This is 10 to 10 to the 0th place, 10 to 1 place, 10 to 2. If we have 10 to 3, we have 1,000, 10 to 4, 10,000, and so on and so forth. Now, this same rule applies to binary. I believe you already know the basis of indices. 2 raised to the power of 0, 2 raised to the power of 1, 2 raised to the power of 2, 2 raised to the power of 3, and so on and so forth. You understand? And I believe you already know the values that this is going to be. If you take your time to calculate it, at least you have calculators nearby, you know the values you get out of it, right? So now you know that this is in binary. The question now is, how high do you think we can count here, just by guessing? In decimal, how high do you think we can count?
I'm thinking it's like 4,000.
That's too high, but let's try it out. So if we want to count 1, this is what? 1, right? You all
Yes,
can
sir.
see
Yes,
this.
sir. Yes, sir.
This is 1. This is what?
10.
This is binary. In binary, we don't actually call them by, you don't call it 10. Understand?
All right.
In binary, it's either 0 or 1. So what are you saying?
0 1 0.
1 0.
Yeah. Ignore because of this first 0. Because of this first 0 is not a 1, you can ignore it. But this is literally 1, right? 1 and 0 is 1, right?
Yeah.
1 and 0
Yes,
is
sir.
2, sorry. Right?
Yes,
Yeah, yeah.
Right? Now, if we were to count 3, what would we have?
1 1
Where
0.
would the next one be? Where would the next
In
one
the
be? What's the
1
next one be?
1 1 0.
No, 110
1
is
0 1.
6.
1 1.
101 is 4.
0 1 1.
Good. 011. Now,
Yeah.
just a quick way to figure what it is out. You can see that this is 2 here and this is 1 here. So you have 1, and it's more like imagine the bulb. Imagine that bulb, but now the bulb is spread out in multiple places. So it's actually on or off, but you know that every one of them is actually a multiple of 2, right? Like up to the power of a multiple of 2 here. So each time you do it, you actually observe that yes, this you can use it to count multiple digits. So now this is 3, this becomes 4, this is 5. If you observe, this is 4 and 1. The 1 is in the 4th place and the 1 is in the 1 place, right? This is 6. 1 is in the 1 place and 1 is in the 2 place. So 4 plus 2 here is 6, right?
Yes, sir.
Hmm.
Can you hear me?
Yes.
Yes, sir.
Yes, sir.
Okay. Now this is 7. This is 7. This is this. Now, if you want to get this, this is 7. I asked before, how high can you count? Now, this is the highest we can count, right?
Yes.
Can you hear me? This is the highest we can count. Now, I want to count 8. Is this going to be possible at all?
No. No.
Given the amount of digits you have here, I want to count 8. Is it going to be possible?
No, sir.
If I were
Not
to actually count 8, what would I do?
you.
You need to add another digit.
I can't do
No.
anything, right?
You.
I
You
have
add
to add
another.
another
Yes.
unit, right? Good.
Yes.
Which, because of like, yeah, that's correct. So now, this is the third one. This is the next one I was added there, and because points at this point, this is full. It can add any other, not add any other thing. Add any other things. If you recall, we used when we're in 100, we stopped 919, right? And for to move to 1000, you need to have a 10 3 raised to the power of. So the same lies here. Everything becomes 0. The 1 is now transferred to this place because we introduced a new bit here. Introduce the new bit here, and this way now you have 8. Now, what you have here is what is called enable. 4 bits in binary is called enable, while a byte is 8 digits, right? A byte is 8 digits. And just for the sake of this class, I would show you what this is like. Now, let me quickly open up a program that I have with me. Open. Mhm. All right. All right, so I believe everyone can see this, right?
Yes, sir.
All right, good. Now, this is just a program that is used to express what I'm trying to say. Now, what you see here are all bulbs, and attached to these bulbs are numbers. But this is 2 raised to the power of 0, 2 raised to the power of 1, 2 raised to the power of 2, 2 raised to the power of 3, 4, 5, 6, 7. Understand? And entirely what you have here is what we have here. We have 8 digits here, right? 1, 2, 3, 4, 5, 6, 7, 8. So now, what is the value of this now? All the bulbs, are they turned on or are they turned off?
Off.
Hmm?
Off.
They're off.
Off.
Are all the values here turned on or turned off?
They are all turned off.
Like, are all the bulbs here turned on or turned off? Hmm?
They're turned off.
Good. Now, good. We want the number 8 here, right? Plus 8. If we want 9, can someone change other bulb with?
So sorry, I
We
didn't
want
get
the
you.
number. If we want the 9, the number 9, what bulb will we put on?
8 and 1 on number 9.
Good. 8 and 1. And what do we have here? 9, right?
Yeah.
Okay. So if you want 10,
8 and 2.
8 and 2. So I'm just going to do the addition here. 10. And this is 11. This is 12. This is 13. This is 14. And so on and so forth. Now, the logic behind this is just simple. Here, you can quickly do the calculations here. 8 plus 2 is 10. Plus 4 is 14. All right? If you do 15, you have 8 plus 4, which is 12, plus 2, 14, plus 1, which is 15. So this is how to calculate this whole thing in binary. This is how binary works. This is how your computer thinks. But the amazing thing is that these things happen very, very fast. Very fast, that you don't know, you do not notice it happen. Now, the more proof is this. When we come down to letters, how does the computer display letters? Now, we have the letter A, capital A, emphasis on capital A, because this is different from small a. And the letter A, according to ASCII, is 65. And 65 is represented this way. Now, if we go back to our bulb example, let's quickly do 65. I'm going to turn this one off, turn this one off. And which one am I going to turn on to make this 65? Which one am I to turn on to make this 65? We'll turn this one off. Now, tell me which bulb. What?
64
What and what?
64.
And 1.
64 and 1.
64
64
and 1. Good. So, yeah. Can you see it? Can you all see the screen, please? If you can hear me, let me know.
Yes, sir,
Yes,
we can
we
see.
can hear you.
Yes,
you can see it. You can hear you.
I can hear you.
All right. All right. So now back to what we're saying here. A is represented as 65. It's called an ASCII. And we have this. Now the ASCII is literally a convention, like it's a format, you understand, to represent letters, and not just letters, special characters. Let me quickly check. I can't recall the year exactly when it was invented, but I would quickly find it. ASCII. Okay. All right, so it was approved as an American standard in the year 1963. Full meaning is American Standard for Information Interchange. It was approved in 1962 standard for computer. So what it's saying now, every single computer follows this standard. Every single computer follows this standard. Now, we say previously. Hold on. Fully this load. Okay. All right. Good. All right. So here, what you see here now are the list of numbers that are associated with each of them. And how this works is that, for instance, if you type the letter A, what happens? The letter A is associated to the number 65. Now the computer understands this by converting the number 65 to binary before it displays A on your screen. Do you understand?
Yes, sir.
The computer treats it by converting the letter A, the number 65 to binary, because the number 65 is already the standard as the letter A. So this is how it works. So this means that if you have these numbers, what do they represent? Please quickly write this down. Quickly write this down. Quickly write this down. Then we'll go back and find out what they represent. Quickly write this down. If you're done, tell me. While you all are doing that, let me write it down too. So, let me do this too. So we have 0, 0, 1, 0, 0, 1, 0, 0, 0.
Sir, this thing is obstructing my view. Your notepad.
Oh, so sorry about that. Okay. 0, 1, 0, 0, 1. Right, hold on now. Just 1 minute, like at 8:13, 8:13 will ask the question. Are you all done now?
Yes, we are done.
All right, if you're done, look at these numbers, look at the numbers you wrote down, and try to tell me what the decimal figures are. Looking at the numbers, Try to tell me what the decimal figures are for each one of them.
1, 3. 3 is
Then we'll test it out here, if it is correct or what? Someone said what? Go on.
4 plus that's
So what and what? The one on the left is what?
The first one I got
Anybody?
288.
Anybody?
The
The one on
first
the
one I
left,
got 288.
what's the decimal form?
288.
288. Wow. Okay. That's what did you get in the second one?
And the one on the left is 72.
Okay. Someone said 72 because 288 is actually wrong. So
8.
72, we'll check it out.
16.
What? 16?
2.
The second one is 73.
32. 64.
I got the
Plus
first one
8.
to be 72.
73, okay.
So, and the last one is 33.
I got the first one to be 74.
No. 1, 2, 3,
The last one
4,
is what?
5, 6.
33.
4.
What's the last one?
33.
64.
33.
42. 72.
33.
7.
All right. Let's test it now. Hold on. Let's come back to this and let's test it out. This out. Now the one is what? What's the digit for the first? 000. Please. What are the digits for the first? What are the digits for the first one? Read it out. Read it out. Read it out. Just read out the zeros and ones that you wrote down. The first one is what?
01001000.
Okay, 01001000, right? And we said someone said 72. So let's cross-check it here. Okay, so we can see that we have 3 zeros here, and we have 3 light bulbs that are off here. Then we have 1, and observe that the 1 is in the 8th place. Then we have 2 extra zeros here, and we'll notice that there are 2 light bulbs that are off here, and we'll have a 1 here, and there's a 1 that is here in the 64th place, and we'll have a 0 here, and we'll have that 0 here. So my question now is, if you observe, how exactly did we come to this? This whole thing was just by figuring out the places, right? The locations of the zeros, or the locations of the multiples of 2, and then adding them up to know the actual answer you want. 64 plus 4 would give us a different answer. 64 plus 1 will give us a different answer. So the idea is to figure out, oh, where is 8 located here for us to get this? Remember that in our in the decimal form, when we're counting in 100, 10, 100, 1000 and so, we actually did it. Okay, the first one is 10 raised to the power of 0 for the units, 10 raised to the power of 1 for the tens, 10 raised to the power of 2 for the hundreds, 10 raised to the power of 3 for 1,000. Right? So knowing that, you already know that, oh, your number is 1. Where would you put 1? You put 1 in the unit. If your number is 123, how would you put it? You do, okay, this is 10 raised to the power 100 times 1 plus 20 times 10 times 2 plus 1 times 3. Because you already know the positions of the digits, right? So the same thing applies here. Now, this is 672, and we have 72 here. So write down 72, everybody, under these digits. Write down 72 under the first binary that we have. Now, the second one is what? 0, 1, 0, 0, 1, 0, 0, 1. So we already have 0, 1, 0, 0. So we also have 1, 0, 0, 1. So this is it. And this is 73, right? Write down 73 in the second binary. The second binary digits that we have. Write down 73. And now this last one is very interesting. We have 001, 0000, then we have 1. So I'll turn off this one and turn off this one, but put on this one. And we have the number 33, right? So the person that said it was right. 72, 73, 33. Now, take note. We have 72, 73, 33. And let's come back to our work. Now, here, remember this. What's the digits here? What is 72?
72 is H.
Hey.
72 is H. Okay, write down H. Write down H. What is 73?
I.
I. Write it down. Then what is 33? 33 is not highlighted here, so let me go to the point where it's
See your
highlighted.
screen. I can't see your screen, please.
Hi.
Can you see my screen?
No, not
Yes,
at
sir.
all.
I can see the screen.
If you can see the screen, if you can't see the screen, it's probably network on your end. Sorry. All right. So now 33 is what? What is 33?
The special character.
Exclamation.
The exclamation mark. All right, fine. So what does everything together is what?
Hi.
All right. Do you now understand how this works? So this is how it works. Code. This is exactly how it works. Down as you have here, single thing here, ASCII equivalent. But as time went on, there were other keys that you could not, and that the ASCII could not cover because it was an American standard, right? Now, if you check, let's say, for instance, Spanish, Russian, bring it down to Nigerians, Igbo, Yoruba, Hausa, and other languages, you know, they all have their ways of writing them, and those things do not appear on the keyboard. So these things now make them to develop a new form that is going to encompass both the ASCII numbers and the new ones that could have special characters attached to them. For instance, excuse me, for instance, something like this. Please disregard the numbers you see here. Disregard the numbers you see here. The numbers are just attached to the numbers of letters here. These are like different variants of the letter A, right? But they all have different numbers attached to them. So we also have emojis. Emojis also got introduced. Emojis got introduced, and everything is actually in something called the Unicode. The Unicode now is like I would call it a big brother, understand? It houses everything. So it contains both everything they're asking, and it extends to especially to newer characters like the letters that have signs on them. You have the emojis, even colors. The Unicode extends to these things. So now that you know this, this is very interesting here. This emoji you see here, this emoji you see here, what number do you think it will hold in the Unicode? Just a random guess. You don't need to know it. Just a random guess.
1.
1? Come on. No, you already know that 1 is taken in from 1 is taken. It's not 1. Higher. Go higher.
1,000.
Go higher.
Wow.
Up to
Million.
a million.
A million. Go higher.
Yeah.
5 million.
Someone wrote what? 0. 4 million. All right. So this right here is the Unicode representation of this emoji. And now we have 1, 2, 3, 1, 2, 3, 1, 2, 3. So it's over 4 million. It's actually up to 4 billion.
Wow.
Understand? So this is the Unicode representation, and this is the binary for it.
Wow.
This is the binary for it. So this is how advanced this.
Chimo.
All right, this is how advanced this has come, and it comes in different varieties. So we have this one's the U plus 1F62. This is like introducing the hex codes to it to shorten this whole thing down. So we have this one, we have this. This is like different colors if you observe. If you observe, the value of this is different from the value of this. This is because of the colors, and I believe you all did colors in CSS, all right?
Yes.
Yes, sir. Yes, sir.
Yes, you all did colors in CSS. So this is actually different. Observe most of them, they all have
Hello?
I can hear you. All right, let's see. All right, so let's see. What do we have here? Let's impute okay, this is necessarily slow. Good. Let's impute this. We had 72, then confirm. No, 72. Can't go higher than this. Very interesting. Okay. All right, let me use this instead. 72. Okay, let's see. Confirm. Here we have next one should be yellow if I'm not mistaken. Okay, green and blue. Red, green, and blue. All right. Here for the green we have 73. 73. Right. Confirm. And for the blue, what do we have here? We have 33. All right. If come on, how do I mix this together? I think I'll just use this one here. And this one is all in hex code. I'm trying to find the one that's not in hex code at all. Let's see. This should work. Now let's pick up just one color here. Remove this. Remove this. Removing this. Removing this. Removing 1 and 2. So let's work with just one here. Good. 72 here. We have 73. This is 73. 73. 72. Oh, it should be 30. Sweet. All right, good. So this is doing something. I'm not sure why. Find. Yeah, and all right, I would actually we'll get back to this. Let's just keep going. I would find that I'll find what I'm looking for and I'll show you what I'm talking about. But the point is this. We'll come back to the slideshow here. The point is that this whole thing here has its own colors, and the colors they have its meaning. And this is as a result of the pixels that are associated with it. For instance, when you guys are doing CSS, I don't know if they ever taught you guys how to like scan each individual pixels to find out the color that is there. Well, you guys taught that. Can you hear me?
No, sir.
All right, let's see if I can just find something quickly.
Yes, sir.
You guys were taught that, right?
No, sir.
I don't
But
really
just do it. Maybe
People
understand.
should pick
we'll understand
Is
it.
it to
to find the colors associated with the colors in a page. To find it. I not thought that is silence. Just show you a quick I'm talking
No,
of.
we have not been taught that yet.
It's actually not a big deal. Something to discover on your own as you're working with CSS. So, good. This Muslim box. What I'm trying to make this. What I'm is this. Observe how this circle has a little black dot inside it, right? And for each place that it crosses, once the black dots hit it, it's like a magnifying lens that checks the pixels itself. On this particular pixels, what is the color here? Now, if you check, when it enters here, you notice that you see FFFF for white, right?
yes.
Can you all see it?
Yes.
Okay. And when it switches to green, you notice there's a color change, right? Can you all see it? Or is it too
Yes,
tiny for
sir.
you people? All right. So now this same thing is actually, this is how tiny these things are in your code, and this is how much your computer processes whenever it's displaying what you needed to display. Whenever it's displaying what you need to display. So here, we'll come back here. Do you all think the computer is a dumb device?
A what?
Dumb device. Do you think the computer is a dumb device?
Yes.
Why? If you think so, why?
Because he cannot do anything on his own.
All right, that's very good. It can't do anything on its own. All right, now, for us to explain this, I would actually give you something interesting to do. The concept of algorithm and how it works. Now, for this particular one, I got a video from TEDx in collaboration with David J. Malan from Harvard, explaining algorithm, and this is what
An algorithm. In computer science, algorithm is a set of things for solving step by step. Specific algorithms are executors, but we can algorithms as well. For instance, know about counting the number of people in a room. Well, if you're like me, you probably pointed them one at a time, count up from 0. 1, 2, 3, 4. Well, that's enough. In fact, let's express it a bit more in pseudocode, just like syntax is a programming language. Let n grow. For each person in room, set n equal to n plus 1. How to interpret this pseudocode? Well, line 1 declares, so to speak, a variable called n and initializes its value to 0. This just means that at the beginning of our algorithm, the thing with which we're counting has a value of 0. After all, before we start counting, we haven't counted anything yet. Calling this variable n is just a convention. I could have called it most anything. Now, line 2 demarks the start of a loop, a sequence of steps that will repeat some number of times. So in our example, the step we're taking is counting people in the room. Beneath line 2 is line 3, which describes exactly how we'll go about counting. The indentation implies that it's line 3 that will repeat. So what the pseudocode is saying is that after starting at 0, for each person in the room, we'll increase n by 1. Now, is this algorithm correct? Well, let's bang on. Does it work for 2 people in the room? In line, initialize n to 0. For each of these 2, we then increment by 1. First trip through the loop, update n to 1 on the through that same loop, update n from 1 to 2. So by this algorithm, n is 2, which matches the number of people. So far, how about a case though? There are 0 people in the room besides doing the count. In line 1, initialize n. This time, line 3 doesn't at all since there isn't in the room, and so n remains 0, which indeed matches the number of people in the room. Pretty simple, right? But counting people one at a time is pretty inefficient too, no? Surely we can do better. Why not count 2 people at a time? Instead of counting 1, 2, 3, 4, 5, 6, 7, 8, and so forth, why not count 2, 4, 6, 8, and so on? It even sounds faster, and it surely is. Let's express this optimization in pseudocode. Let n equal 0. For each pair of people in room, set n equal to n plus 2. Pretty simple change, right? Rather than count people 1 at a time, we instead count them 2 at a time. This algorithm does twice as fast as the last. But is it correct? Let's see. Does it work if there are 2 people in the room? In line 1, we initialize n to 0. For that one pair of people, we then increment n by 2. And so by this algorithm's end, n is 2, which indeed matches the number of people in the room. Suppose next that there are 0 people in the room. In line 1, we initialize n to 0. As before, line 3 doesn't execute at all since there aren't any pairs of people in the room. And so n remains 0, which indeed matches the number of people in the room. But what if there are 3 people in the room? How does this algorithm fare? Let's see. In line 1, we initialize n to 0. For a pair of those people, we then increment n by 2. But then what? There isn't another full pair of people in the room, so line 2 no longer applies. And so by this algorithm's end, n is still 2, which isn't correct. Indeed, this algorithm is said to be buggy because it has a mistake. Let's redress with some new pseudocode. Let n equal 0. For each pair of people in room, set n equal to n plus 2. If one person remains paired, n equal to n plus 1. In this particular problem, we've introduced in line a condition, otherwise known as a branch, that only executes if one person we pair with another. And so now, if 1 or any odd number in the room, algorithm will not them. When we do here, well, in 3s or even 5s, and beyond that, it's a little bit different points. End of the day, whether executed by computer or humans, algorithm is just a set of instructions which to solve these were solve.
All right. So back to it. Now, the basics of algorithm is literally ways to solve a problem. You understand? Step by step ways to solve it, instructions to solve a problem. The concept of programming is actually instructing a computer to do something. Now, there is something that goes on most times. I noticed that, oh yeah, you guys would run into an issue because your code is not displaying. You understand? Maybe you run a HTML code or you try to run a CSS file. You want to implement something from CSS and it did not display well. And you tend to think that this is the computer's fault or the browser's fault. But that's the thing. When you go back to take a look at it, you observe that this thing is actually something you told the computer, and this is what you told it to do. This is how it was able to understand it. You did not express it properly. I believe you all have experienced it. I mean, some people have come to my DM to tell me that, oh, their image is not displaying the way they want it to be and so on. But when you check it, it's not like they pointed it correctly. So the computer was only looking at what they pointed, right?
Yes, sir.
All right. So you all have experienced this thing. So you understand now that the computer only takes in it only gives you what you give it, and that is what this algorithm is. This black box that is here is what the algorithm is, and it's where the code. It's just a long way to say code. Now let's use a phone book for instance. Now you have your phone book. You have a way of searching for your contacts, right? By default, thanks to technology, you can just search and it's going to implement some code in the background and match it to see if anyone matches. And if it matches, it's going to display the contacts for you. If it does not match it, it will tell you that this contact is not found. If you decide to search by numbers, it displays it, and if it doesn't exist, tell you that this contact is not found. Now, let's assume that we're looking for something like Mike Smith. And going back to what the algorithm is, let's assume, no, let's use a dictionary for instance. Let's also use a dictionary for instance, because the dictionary is actually very simple. Let's say you're looking for a letter. Let's say you're looking for a word. Someone give me any word quick.
Letter.
Letter, right? Good. Letter. Let's look on something. How would you use an algorithm that run that? Would open this notepad and do it. Now, how would you implement something that's going to do it? Talk about it. So, what's the first do?
Check the first letter.
Check the first letter. Okay. Say first letter. Check the first. Okay. Someone else should say something. We are looking for let's do pseudocode on to find the word letter. Okay, so he said first letter. That's what he said. Okay, so tell me, somebody else should say something.
When you find out the first letter, you can now go ahead and check for the second letter.
You find the first letter, check. Let's use a condition. If first letter is found, check for second letter. Okay. So how we are going to be doing by one.
Sorry, I didn't get you.
Is this how we are going to be doing it one by one? Like, is this how, like, us, you should understand something. This is an instruction you are giving the computer. Do you understand me? And because it's an instruction you're giving the computer, you have to consider that, oh, there is time here. You understand? Time is also a factor to consider. This now is not complete. This is not complete in any way. What you're telling the computer to do literally now is that it should go to the dictionary and look for the first letter. If the first letter is found, look for the second letter. What letter is it looking for? You understand me? What letter is it looking for? You tend to forget that the dictionary itself has letters all over it. So it could go to the first page or even the cover page if I just pick the first letter and pick the second letter, and it assumes that it is correct.
Yes.
Do you understand me?
Yes.
So this is not a way to go about it. Scratch this out again. How do you go about this?
Look for letter L.
You say letter L. For letter L, I'm going to put that. Let's just use this. Okay.
Then the second one is it will check for letter E, letter T, and R.
So meaning now is then check for the next letter in the word. This is what you are saying, and it is going to keep doing this. Now, how does this end? How does this program end?
By printing out all the letters when they are
By
found.
printing out all the letters, so print out all the letters, fine. Now let's do print all letters found. Now, how do you think the computer is going to respond to this? Because like this now, it says look for letter L. Even if the computer sees something like aluminium, what do you think will happen? Is that not letter L?
Yes, sir.
Okay, so how do you fix that? Do you see that? Do you see that this is wrong?
Yes, sir. Oh, wow.
Yeah.
Okay, we can tell the computer to check for a word that starts with letter L.
Okay, look for this is getting better. Look for a word that starts with letter. This is yes, let's L. Okay.
That same word, the next letter E.
Then sure. And this. No, you're not saying correctly. So like same word. Look for
Not same word though, like any word.
okay word. Letter E, right?
Yes.
Okay.
Yes.
Okay.
Then in word, look for letter T.
After E.
After E, yes.
Word. Look for T.
He wrote I.
You said any word, so
No. Actually, what I'm seeing is I instead of T. Is that
all right. I think this is actually a bit difficult. We'll come back to this. Let's do something different. Say you want to cook This is something like YAM, and you want to instruct the computer on doing this. How would you give the computer the instruction?
Let's say look for a word that starts with Y.
I know, I said you are instructing the computer to cook yam. You're not telling it to look for Y.
Okay, to cook yam.
Yes.
Boil water. Okay, peel the yam. Or is it boil water?
Okay. Peel the yam. Next one is what?
Wash the yam.
Wash the yam.
Then set the pot on fire.
That's the pot of interesting. Very good.
Boil water, very good. Don't go bump the house.
All right. Boil water.
Put the yam in the boiled water.
Okay. Put the okay.
Wait till
and cook.
Cook, right? Okay.
Yes.
So now, let's break this down. We have a tuber of yam here. The first step is to peel the yam, right? The second step is to wash the yam. Assuming there were two tubers there, you guys did not state the yam that is to be washed. So assuming there were two tubers there, it could peel the first one and wash the other one that is unpeeled.
Hey, Jesus.
Jesus.
You understand? Now, you said someone said set the pot on fire. You see how beautiful that statement is? You understand? Set the pot on fire. Then another one says boil water. Where are you boiling the water? Are you boiling it with a plastic? Are you boiling it? What exactly are you boiling it with? You understand? Do you see how it is not like, as much as to the human mind, it is very, very easy to understand, right? But to the computer, you have to be very, very specific on the instructions you are giving it. Do you understand me? You have to be very, very specific on the instructions you are giving it. Now, you say put the yam in the boiled water. Let us not forget that this yam in question has not been sliced.
Because it's now. Okay.
Yeah. Let us not forget that the yam in question has not been sliced.
Exactly.
Put the yam in the boiled water, and the next thing is cook. You understand? And it's just going to be on fire. It's going to burn. No point where it's
almost. This is critical thinking. No.
So literally, the reason why I'm saying you're going to JavaScript is not as easy as CSS and HTML. It's completely different. You understand? It's completely different. You have to think it. I want this computer. That's why I keep pointing out you did in HTML. Those errors that you made, were they errors that the computer has made, or was the computer just taking the instructions you gave it? Because that is just the easy way to solve this whole thing. Once you know that, oh, this particular thing now, I'm the one that made the mistake. I did not give the computer the right instruction. It's bound to give this error. So you have to look for where you made the error. Do you understand me? Do you see how this is actually looking simple to you, but when you want to give it to a computer, you have to think critically to know that, okay, this is what I want the computer to do. Do you understand me?
Yeah.
So now, we'll come back to this. I would show you another video on what it is like to do in pseudocode. Now, this is this is a video from CS50, and it's actually a demonstration of computers and how to give them instructions. Now, take a look.
They are computers computers. And computers, at the end of the day, are actually pretty dumb devices. They're super fast, but they can only do literally what they are told. You can't just say make a peanut butter and jelly sandwich. You have to program them to do that. You have to tell them with precision what to do, lest things go horribly and hopefully amusingly awry. So with that said, we need one call out from the audience for what should step 1 be if the goal here is to make a peanut butter and jelly sandwich. Yes. Open the bag of bread. So if the 3 contestants would like to proceed to do that, literally open the bag of bread.
It's not about he said he was putting his hand for you not to eat it.
So let's work on that. All right.
Brush hit my hand. He didn't touch your hands.
Please, Chinechere, please.
Before you use that, he touched your hand. So my hand was like,
Hey, what noise is this now?
What's going on, please? Going on. All right, let's go, please.
2. Let's take this further. Yeah, in the front. What's that? Remove the bread. Similarly succinct. Thank you. That's it. Okay, so step 2 is going to be remove the bread. All right, someone want to write us a longer sentence? Someone else. A little more commitment. No, nothing now. Yes. Place 2 slices next to each other. Place 2 slices next to each other. Step 4. Yes. What, say that again? Next to the peanut butter. Okay, progress. Step 5, excellent. Yes. Pick up knife. Okay, step 6, yeah. Hold knife by the handle. Hold knife by the handle. Step 7, yes. Put knife in, I heard put knife in peanut butter and take as little as possible. But all right, step 9. Step 9. We haven't made a sandwich yet. Yeah. Using knife, peanut butter, apply peanut butter on. All right, step 10. Step 10. Yes. Step 11. Step 11. Step 11. Come on, yeah, right there. Carefully pick up jelly. Okay, and then another hand was up. Right behind you, yep. In blue. From jelly. And there. Production of it. Step 14. We're almost there. Yes.
Invert jelly bottle before everything falls out.
Invert jelly bottle before jelly falls out. Step 15. Replace the cap. Step 16. Yeah. Say that again. Up your jelly. So really, go. Oops. Come on. Replace the cap. Put cap. You said remove cap from jelly. Feel like we're in a bit of a loop. Step 17. Yes. Say that again. Go back to step. Remove cap from peanut butter. Yes. Drop all the jelly on the bread. We're almost there. Step 19. Why don't we one step to take this more step and then serve sandwich? Oh, any switch means let's indent it. Eat. Congrats, thank you for our volunteers here. Fred, to bring back home. Thank you.
All right. Do you understand what we're talking about? Can you hear me?
Yes, I can hear you.
All right. So do you?
A kind of
Did
a
you
step-by-step guide on how to.
exactly
Mm.
go on how to do what?
On how to like have your delicacy, your bread.
No, what's happening here now? Someone's mic is actually all right. So what happened here? Chikudi.
Please, Chukudi.
Chikudi, please mute your mic.
It's Chukwemele.
Okay.
Oh, Chukwemele, mute your mic. Oh, you know you're the one. Good. All right. Now, what happened here is this. The three people that were acting as the computer, right? And people in the background were giving instructions to them on how to make a peanut butter, a peanut jelly sandwich, right? And if you observe, the guy in the center was taking it literally as they say. Remove the bread, and the bread was removed from the table. Do you understand?
Yes, sir.
Now, this same thing applies to this line here. Set the pot on fire. You understand? Applies to this same line here. Wash the yam. What yam are you washing? Applies to this thing here. Put the yam in boiled water. Boil water. You observe that these things, we take them for granted because we understand it. But for computers, you have to go out to be specific. You understand? Go the extra mile specific and instruct given the computer. Otherwise, things will and you won't understand. Do you understand?
Yes, it is becoming clear.
All right. So now let's come back to this. Now we talked the dictionary. Let's assume that we are looking for the letter, the word letter, right? Now, your first step could be, let's see. Now with this, can you guys just tell me the first step that we should take here? Anyone? Anyone?
Open the dictionary.
Open what?
The dictionary.
Okay, good. Open the dictionary. Let's make it clearer here because we would actually soon run out of time here. Open the dictionary to the first page. Dictionary to the first page. Now, the second thing is you want to search for the word letter, right? You want to search for the word letter. If word not found, if word is not found, what happens?
Replace dictionary.
If word is not found, what happens?
If it's not found,
Move to the next page.
Very good. Move to the next page. Go to next page. Okay. No one is saying anything. What do we do if we don't find it?
you will still open another page. If we don't find it in that second page, we'll go to the third page.
No, that's not a good instruction because you're saying the computer is meant to look for it first. Do you understand me? Like I said, you are giving the computer the instruction. So how do you make the computer go to the next page? Or how do you make the computer search for that word first? It's simple here. We just go to line 2. Let's see. Go to line 2. And what is in line 2?
Search the word letter. For the word letter.
Search for the word letter, right? Okay, good. Now, what happens if it doesn't find it? It goes to the next page. You see how this whole thing goes on, right? Now, let's add a new condition. Else. If word is not found. Turn it off, please. Word is not found. 7. Stop. Stop searching. Now, who can tell me what this means?
I don't understand what it means. How? Is it in terms of the dictionary not finding the word later?
Exactly. Exactly. So this is based on the assumption that if the dictionary does not find the word later, it stops its search. Do you understand me?
Mm.
Now, would you say this is a fast algorithm?
It's not a detailed algorithm, like, I don't know how to explain it, but for me, it's not. I'll put it as a fast algorithm.
It's fast.
Can
Can anybody explain? Can anybody? And shallow. Okay, why is it shallow?
Because had it been the person typing it instructed the computer, let's say if you couldn't get one of the letters, alternatively check for the second letter. I don't know, I'm confused. I don't know how to.
All right, fine. All right, so maybe we should try a different example. Let's use a phone book instead. Do you understand? Let's use a phone book instead. Imagine your dictionary. Let's use a phone book so that it would not stress you out or it would not make it confusing for you. Open the phone book. Look to find the name. Let's see. Let's use Smith, right? And you know how you say your names, first name, then last name, appears first name. Search for, we are looking for Mike Smith. Mike Smith. So now, open the phone book page, search the word Mike Smith. If the word is not, go to the next page, then go back to line 2. If the word is not found, keep going to the next page. Else, if the word is not found, stop searching. Now, we forgot to add something here. Who can tell me what it is? There's something we forgot to add. All right, let me help you out. Now, we forgot to add a condition that shows that, oh, this computer, if it finds it, it should call Mike, or it should show that it has found it. You understand? In other words, it should print or something. You understand? So if it finds it here, so it goes to, go to line 2. Yeah, this is supposed to be 6. Let's make this 6. If Mike Smith is found, Mike Smith is found, call him. Let's see. So 7, this will be 8. Good. So now we showed that, okay, if Mike's found, we should call. If not found, we should stop. We should keep going until it stops. Right? Now, let's see. Go to the next page. This is supposed to be. Oh, this is okay here. It's okay here. All right. So now let's work on this. Let's work on what we have here. Let's work on what we have here. This should be 7 because we are calling him. And this is 8. Right. So this is all right. Now this is not fast, to be clear, because this means that we would have to be flipping each page one by one to search for Mike. Do you understand me? We have to be flipping each page one by one to search for Mike. So how do we make this faster? As we want to make this faster, how do we make this faster?
Is it going randomly? Searching it randomly instead of
Going randomly is going to be a problem. How do you tell the computer to search randomly? Are you going to tell it to move to page 5 or go to page this and after searching for page 5? How do you do that? Because you might not even know how many pages are in page.
Okay,
You
let's
might
say,
not know how many pages are in the phone book.
okay, let's say for instance, if the pages is 100, if we have like 100 pages, we can now instruct the computer to search from page 1 to 100.
To look for Mike. Remember that this computer is meant to be, you're flipping through it. It's a phone book. You know what a phone book is like? Imagine a phone book like a dictionary. You are flipping through each page to look for a particular word. Right? So in this case, in this context, you are flipping through each page to look for a particular contact.
Okay.
So let's try a different. You think this is faster? Open the book this page and see word Mike Smith. Let's copy and paste again. So the first page, word Mike Smith. If the word is not found, to next 2 pages, search for the word Mike Smith is found. Call him. Else is not found. Stop. Do you think this is faster?
Yes, it's faster, but mistake can be made. Mistakes.
Good. It's fast, but it's not accurate. So what is the mistake that can be made?
Those 2 pages you are skipping, the word can be found there.
Good. So how do you fix it?
How about we divide like from A to Z, we divide it into half. Like we give it a range.
All right. So let me quickly do this. Let me quickly do this. Slow but accurate. The comment. Here we have all right. So that's the first one, slow but accurate. Second one is faster than first one. Faster than first one, but inaccurate. Right? Now, the third one. Now, the third one says what? What did you say is the third one? What did you say is the third one?
No, you know the way dictionaries and dictionaries are arranged, like from letter A to Z.
Okay, so
Now that's saying that we can split it into 2, like from A to P. It will check
okay,
the
good.
first
The
letter
first one.
if it's from range.
All right, good. Now let's do it. Now, so say split book into 2. Search for the word Mike Smith, right? Or what do you do next?
Actually, if I'm actually lost. Like the
All
first
right,
letter.
let's make this simple. Okay, we look for the first letter, right? M. Okay.
Yes.
Now
M.
split the book into two. Let's search for the first letter. So assuming the letter, let's say search for the word, search for the letter M, or let's search for the word M and Mike Smith. Now, because of this is in an orderly fashion, right? Because this is an orderly fashion, it means that if we search for the word Mike Smith, what this means is that we will actually check. There's a possibility that we could fall either closer to Mike Smith or farther from Mike Smith, right? Basically, what your algorithm states is that if you split the book into two, there's a chance that you could land in the P section and the Q section, and you check, or let's say you land in the P section, you have Patrick and so on and so forth, and you need to check for Mike. Where would you be looking towards the left or the right?
Left.
Towards the left. So now, if word is not found, what you know is that go to the left side of the book. Then what next should you do again?
Then we can use that our first code and be searching it page by page.
Exactly. So you do split book into two again, right?
Yes.
You split the book into two again. Now, if you split the book into two again, what happens? This means that you have actually you've done this divide and conquer method. You split it into two and you check. Perhaps you landed in let's say G, in section of G. Now G and M, where will M be falling towards? The left or the right?
The right. The right.
The right. Good. The right. So it means that you do away with
The left.
the left part of the book, right? Okay. So if Mike Smith is not found, let's see, go to the left. Let's just use go to the left or right side. Right side of the book. I'm doing this because of time. Time is not on our side. So now, if Mike Smith is not found, he goes to the right side. It's just closer to Mike Smith. Okay. So if Mike Smith is found, you call him, else you don't call him. Now, what does this mean? This means that you keep splitting the book into two until you find Mike Smith, right?
Yes.
Let me, okay, just to clear up the air, let me quickly open up the example or a demonstration of this, if you don't mind. All right, so this is also a different video, but still talking about this whole thing that we're talking about, the pseudocode. So let's do it again now. Please, I want you all to pay attention because this is going to be very
Increasingly hard
important
to
for
find,
everyone.
but this isn't producing another thing, full phone book, inside of which are 1,000+ pages of names and telephone numbers. And if I wanted to look up someone in this phone book, I could simply do a very naive algorithm. I could open up to the first page and I could start to look for, say, someone named Mike Smith. And if he's not on the first page, I progress to the second, and then to the third, and then to the fourth, and so forth until I finally find Mike Smith. Now, is that algorithm correct? Yeah, if he's in there, I'll eventually find him. But it's arguably not very efficient, certainly not fast, because my God, why am I wasting my time flipping through all of these pages when I could certainly do this physically faster? Well, a slight optimization, so to speak, might be not 1 page at a time, but 2, 4, 6, 8, 10. Still correct? So it's no if I, for instance, skip over Mike Smith, but so long as I backpedal 1 page, if I overshoot him, maybe we could correct that otherwise, that what might otherwise be a gotcha. But is it better? Is it faster? I mean, yeah, it's literally twice as fast if I do 2 pages at a time. So if I originally had 1,000 pages, now I only have to flip 500 times, not fully 1,000 pages to get potentially, in the worst case, to the end of the phone book where someone like Mike Smith or someone with a later name might actually be. But of course, we humans certainly aren't going to be doing that, certainly not at this point in our lives. What is a reasonable human likely going to do? Go straight to the S's. How do I go straight to the S's? Well, there's no marking. So if there were indeed a label or a sticky tab for S, we should jump right there. But it's pretty innocuous. So the best I can do is, roughly to the S section, or maybe roughly into the middle. But the key takeaway now, and the intuition that you've sort of taken for granted for years probably, is that what do you now know about this problem? Mike Smith is surely not in this half of the problem, because Smith comes after the middle, which is roughly the M section, it seems to be. So as you might have seen at Visitas, we can now literally tear this problem in half. It's getting easier and easier. There you go. It's fundamentally the same problem. It's literally half big. I'm still for Mike Smith, and our say I can still the same way. The problem in half and tearing again in half now leaves me with the quarter of the side. We throw that away and repeat this process and again, glancing down at each to see if Mike is on the page in question. Now, if I do this, ultimately I'll find with just a page. Mike Smith is in the. Of course, I can call Mike again, but the point is that if we started with 1,000 pages, my first algorithm flipped the page maybe 1,000 times. Definitely less because it's an S name and not a Z name, but as many as 1,000 pages potentially. Second algorithm, better, 500 pages. Third algorithm, though, how many steps would it take to divide a 1,000-page phone book in half like that? 10, give or take.
All right, so do you now understand this? Like, do you understand the demonstration now, what you're trying to say from the demonstration? Do you all understand, what's his name? Sorry. What's your name? Let's see. Chibi, do you understand Chibuike's solution here now?
Yes.
Do you all understand Chibuike's solution? So it makes Chukwemele, I think you should be the only one that is not responding, please, because your stuff is echoing a lot. Maybe just react. Other people can respond. So you see that this particular his solution actually splits the problem into half. If you observe, everything was split into half and it made the work easier and faster. And if you check, our first algorithm was the one where we had to be checking each page one by one. You observe that it took time to solve, right? Like if you watch, it takes a longer time and you progress slowly, right? The second one was a bit faster because we're going 2 pages and just go back 1 page. We go 2 pages and go back 1 page. Now, the third one is different because it comes in with a faster form of doing checking it out. If you check, it's a log graph. Now here you observe that this actually takes lesser time. If you check from here, if you check from this place, it takes lesser time compared to the first 2 algorithms, which is actually what we observed here. You split it into 2. Let's call it divide and conquering method. Divide and conquering method. It splits it into 2 and it takes the lesser time to solve it. So you see how easy this is, right? Now, move on to the next thing. So this is actually called a pseudocode. Now check, this is the pseudocode for what we're trying to do. Pick up the phone book, open to the middle, look at the page. If person is on page, call person. Else, if person is earlier in the book, open to the middle of the left half of the book. Right? Open to the middle of the left half of the book. Go back to line 3, and this is line 3 right here. This is line 3 right here. If person is if person is later in the book, open to the middle of the right half of the book and go back to line 3. Do you all understand how this whole thing is going on now? Do you see how this whole thing is going on? Else quit. Now, why are we quitting here? Can anyone tell me why we are quitting?
So the code does not run for an infinite period of time.
No, that's not why. We are quitting because that actually is correct. That is correct. That is logically correct. But we are quitting majorly because of we do not have this. This is where the code ends if we don't find it, if we find the person. Do you understand me? If we find actually do based on certain situations or certain circumstances. For instance, you want to go outside. You check the weather. If the cloud is gloomy, you take your umbrella because it might rain, right? Else, you go out. If the cloud is clear, it means there will be no rain. So these are conditions. So this is literally what it is. If the cloud is gloomy, take your umbrella. Here, if the person is on page, call person. Yeah, if the person is on page, call person. Everything you see here, the first set of things, the ones on yellow right here are verbs. They are like functions, you understand? Do this, do that, do this, do that. You understand? While the if, else are called conditions. You understand? These conditions are things that things that have to be achieved for certain things to be triggered. Okay? Now, here we have loops. We have loops here. You check if person is on page. These are the completions of the conditions here. First one, if this person is on page, this is a condition here. This one is a condition here. This is a condition here. You understand? Person is on page is a condition. Person is earlier in book is a condition. Person is later in book is also a condition. You understand? I'll go back to line 3. This is like a loop. Understand? A loop is like repeating a pattern of a certain number on you find it. You understand? Let's take for instance. Let's do it. This first one. Have pick up book, middle of phone book. Look at page. If person is on all person is in end book. Go to middle left half of the book. Then go back to line. Now, line 3, please tell me what happens. When we go back to line 3, what happens next? Can anyone tell me?
Is it when the person is not found?
Now, what is? No, I'm talking about this condition here, number 8. Lines 8 and lines 11, the ones highlighted in yellow, they state go back to line 3. These are loops, right? It repeats itself until a particular condition is satisfied. Do you understand me? It repeats itself until a particular condition is satisfied. Now here, it says, look at page. If person is on page, call person. What this means is that if you go to the left half of the book and the person is on page, you should call the person. If the person is on the right side of the page, check again. You understand? If the person is on page, call person. You keep doing these particular things because these are like They are loops and conditions. Basically, if so and so is happening, do this particular thing, else so and so should happen. Let me extend this again. Now here, it brings us to functions, conditionals, and Boolean expressions with loops. Boolean expressions, we've explained loops already. So conditionals are literally the if-else statements. I used the rain to give an example. Functions are verbs, like in English, they are like verbs, you understand? We are to do this, we are to do that, we are to do this, we are to do that. You understand? Boolean expressions are literally associated with conditions most times. It's either this or that. It's either 1 or 0. You understand? It's either truth or false. Do you understand me? This is what it's like. Boolean expressions: truth or false, 1 or 0, this or that. Do you understand me? So this is what it's like. So here, we don't have time again. I would have loved to show you a graphical demonstration of what it's like, but I think I can just do a little bit, depending when. Excuse me. Oh wow, my battery is actually low. I would have loved to actually give you guys a graphical demonstration of what it is like using this, but perhaps in your next class you'll be able to do it. You understand me? In next class, you'll be able to do it. So, do you guys have any question?
Yes, please, I have a question.
All right.
Please, I did not join immediately when the class started because of network. Please, which app are you using to like
Which app am I using to do what?
you type all these things, please?
Oh, I was using Notepad to do that. It's not this. It's not Notepad that we use. It was like you won't use Notepad to do it.
Okay, we should use VS Code to do our own.
Your VS Code. What I did was basically pseudocode. Pseudocode are just human language. You understand? They resemble human language. Understand? So when you're using VS Code, you are going to type the actual code. By the next class, you'll be taught Java. They will introduce you all to JavaScript properly, and they will teach you all the syntax and every other thing. But you will get to see the logic that I was trying to explain to you applied there. Do you understand me? Get to the logic
Okay, sir.
applied there. You won't have to be typing this. But here is actually what I think you would do. For the time being, when you're working with things, different projects, the first thing you want to do is to understand what this is about. What is the instruction I'm about to give this computer? Do you understand me? Recall that YAM example that we tried, the YAM pseudocode we tried to do. Recall the dictionary pseudocode we tried to do. Recall this phone book one that we just saw the demonstration of it. Do you understand me?
Yes,
And
sir.
try to do it. For instance, just for fun, you could even try out a guessing program, a program that can guess your number from, can guess a number from 0 to 9. You understand me? You can try it
Yes, sir.
out just for fun. Try building a program that can guess your number from 0 to 9. And a way to do it is literally this divide and conquer method that we did.
Thank you, sir.
Okay, so the next person, please ask your question.
Please, I want to ask, is it possible for you to send us those clips, those video clips? Uh, he has disappeared.
Oof, his phone is low. Maybe
Yeah.
just drop the
Yeah,
message.
I'm
Just
still
drop the
here. I can
message.
hear you. I can hear
Okay.
you.
Okay. Sorry.
I can hear you. So I'll try my
I
best
said,
to do that, to send you the video clips as explanations for these things.
all right.
Thank
Thank you
you.
so much, sir.
Thank you,
All right,
sir.
any other question? Any other question, anybody? If you have any other question, ask, please. All right. If you don't have any other question, I think this will be the end of the class. So goodbye to everybody. I hope this was fun because the next one now you're meeting is JavaScript. The next class you'll have will be JavaScript. Hope this was fun.
Yes.
Yes.
All right. All right then. Good night, everybody, and sleep
Night.
tight. I guess. All right. Bye.
Bye. Thank you.